Assalamu alaikum. This lecture is again related with the application of differential equation, that where these differential equation has been used in the real life problem. So there are many problems, many real life problems. Just Newton law of cooling. This is a epidemic problem, and here I have first taken this problem. The name of this problem is dynamics of SIR model. Okay, the dynamic of SIR model. So now I will explain this XIR model. Suppose we have a population n. If total population, you can say total population of the world is just like 7.5 billion, and I am focusing on it on a limited population. Suppose this is a total population of a city or total population of a country, and let this is equal to n. So this topic is about an epidemic disease. Okay, that disease which is transferable from one body to another body, and let this is the total number of people. This is the total number of people. Initially, all the peoples are called susceptible. Initially, all the peoples are called susceptible, that every people or everybody has a chance of a disease. He may be infected from a current disease in a pandemic situation or in an epidemic situation. So each has so it can be written as S is a function of time. Okay, suppose this person got a disease. Okay, so he has been infected. Okay, this person is now infected, so he can infect this person, he can infect this person, he can infect this person. So in his radius he can infect any other person, and let this is denoted by I. I is the number of infected people in this population. Okay, when he got infection, then suppose these population got infected. Now each of the infected person has the chance that he may recovered, he may died. Okay, so here R represent the recovered people. Okay, R represent the recovered people, and also are included the died people, the people who get died because of this population, because they cannot affect any other person. So we have logically put it in the dead people in this function. Okay, so what ds by dt represent? Ds by dt, this represent the rate of change of the susceptible people, that how this change with respect to time. And here di by dt represent the rate of change in the infected people. Okay, and dr by dt, this represent the rate of change of the recovered people. So you know that logically this rate of change is directly proportional to the product of S and the product of I. It is directly proportional to the product of S and I. If S are larger and I is larger, so this rate of change will be even much larger, and this beta is constant of proportionality. And now here this rate of change in I, this is directly proportional to the product of S and I. So this is again this is the same constant beta and minus Ri, and this is another term, and this is the third differential equation. These are, if we see clearly to these equation, this is a first order, this is a first order non-linear ODE, and this is again first order non-linear ODE, and again this is a first order ODE, So combinedly these three are called system of ODE, system of first order ODE. So here I am not solving, I am just modeling these differential equation. I am just telling that where these differential equations are have been used. Okay, so I am not here I mean I am not concerned with the solution in this segment. So we can apply these differential equation in any epidemic disease. This SIR model is a very popular model in the world. S stand for susceptible, I stand for infected, and R stand for recovered people. So we can easily solve this system by some software, some by mathematical I mean exact solution, some analytical solution, and sometimes we can solve such a problem with numerical methods. And now in the current situation, as we know that this corona disease is COVID-19 is an epidemic. Internationally it has been declared that this is an epidemic disease, and we can also apply this SIR model with some modification. Okay, with some modification. The first modification will be the S. You know, this susceptible population is not constant because in the birth of newcomers, because of the birth of the new people, and this, and also R is also affected by the natural birth of the given population, and these beta and gamma are such constant which depends on what? Which depends on social distances. This beta depends upon the it is a function of stay home. It has been declared that it is a function of stay home, and make sure that CDC is also working on this model. CDC is Center for Disease Control in America. It is in United States. Give a very accurate data for such a problem, such population model, and they are working on this parameter. In fact, in the current situation, the beta is very high. So for an effective model, we should reduce this beta to as minimum as possible. And now we can modify these problems, these differential equation, the model of SIR with any other model. Okay, so just I was given you the flavor that where this differential equation has been applied. This is one of the very good application of the differential equation.